So the next concept we want to discuss is the concept of improper integral. So before we go to improper integral directly, consider the following problem. We have curve y equals to 1 by x squared, y equals to 0, and x equals to 1. So the curve y equals to 1 by x squared is given by this curve in the red. And we have y equals to 0, which is the x-axis. And we have x equals to 1, which is this part here. And we want to find out all this area. What is the area here? That is the idea. So let's first see area for below 1 by x squared from 1 to 2. So that is given by integral 1 to 2 1 by x squared dx, which is same as minus 1 by x from 1 to 2. That is going to be minus half plus 1, which is going to be half. Let's do the similar calculation for this part here. In this case, it will be integral 1 to, instead of 1 to 2, it will be 1 to 3, 1 by x squared dx. And again, this will be same as, instead of this, you have 1 over 3 plus 1, which is 2 by 3. Similarly, for this part, we have integral 1 to 5, 1 by x squared dx, which is going to be minus 1 by 5 plus 1, which is 4 over 5. If we proceed this, here we want to find out integral when the interval is infinite. So it will look like integral 1 to infinity 1 over x squared dx. But hold on, before writing a thing like this is not a number, right? So first of all, this writing, although intuitively it makes sense at the moment, it's not even defined in our proper setup yet, right? So we want to define what this is, or is such an object even possible? Because until now, our integral is integral a to b fx dx, right? Where a and b both are numbers, but infinity is not a number, right? So what do we mean by such a thing? I mean, of course, intuitively it makes sense because we want our interval to keep on going forever, right? So what is this object? Yeah, so let's define this thing. And such a thing is called improper integral. Why? Because one of the limits is not even a number, right? So here is the improper integral. It is called improper integral of type 1. We'll see type 2 to understand why we call it type 1. So what we want is, we want to define integral a to infinity f of x dx. Now, one way to deal with infinities, or actually all the time, the only way to deal with infinities is to use limits. So we have limit as t goes to infinity of a to t f of x dx, right? This is how we can approach infinity. This number is well defined because for every t, it is a proper integral, and you take limit of it, you get an improper integral. So let's define this properly. So integral, if a to t f of x dx exists for all t greater than or equal to a, right? I mean, before we define this, it should exist. So limit at x go a limit. So integral a to t f of x dx exists for every t greater than or equal to a. Then we can define integral a to infinity f of x dx is equal to what? Limit as t goes to infinity of a to t f of x dx. Yes, you're letting this go to infinity. Yeah. Similarly, if you have minus infinity to b f of x dx, you want to define this guy. What should happen is, if t to b f of x dx exists for every t less than b, then minus infinity to b f of x dx is basically limit as t goes to negative infinity t to b f of x dx. So the idea is you deal with going to infinity via limits, and that's the proper way. And this is the definition. Now, suppose, so integral a to infinity f of x dx and integral minus infinity to b f of x dx are called convergent if this limit, after all, these are limits, right? This integral is a limit. So we call them convergent if the corresponding limit exists. This limit exists here, right? So if this limit exists, then we say it is convergent. If this limit does not exist, then we'll say it's divergent. Now, suppose we have minus infinity to a f of x dx and a to infinity f of x dx, both are convergent, then we can define minus infinity to infinity f of x dx is minus infinity to a plus a to infinity. Okay? So this is how we define when from minus infinity to infinity. Okay? And this a can be any number in between. You can pick a to be anything in between you like, as long as that is convergent. So let's work on a problem. So problem 1a, integral 1 to infinity dx over x. So first things first, we need to write down what does it really means. It means that we have limit as t goes to infinity of 1 to t of dx over x. That is what it means. So this is the definition. This part is definition. Now you compute this limit integral. This integral of 1 over x is what? Minus, so integral of 1 over x is ln x 1 to t, limit as t goes to infinity. Generally, you take ln of absolute value of x, but since we are in 1 to t and it's positive, right? So I can get away with just writing ln x. So this is going to be limit as t goes to infinity ln t minus ln 1. ln 1 is 0. And what happens as t goes to infinity? Where does ln t goes to? ln t goes to infinity. So therefore, this integral is divergent. Yeah, it diverges to infinity. It is divergent. Let's look at the next problem, problem B. So for problem B, we have integral 1 to infinity of dx by x square. Again, by definition, this is same as limit as t goes to infinity of 1 to t of dx by x square. Okay, so the first thing is always to write down the definition here. Okay, that's how we can deal with infinity via limits. So this is going to be limit as t goes to infinity. This integral is minus 1 over x, 1 to t. This is going to be limit as t goes to infinity, minus 1 by t plus 1. Now as t goes to infinity, this will go to what? Minus 1 over t will go to 0. So we get, this is 1. So therefore, this integral converges or is convergent. And what is the value? And the value is 1. So this is how the the definite, the improper integrals are gone. Now let's look at the next one. So here, problem C. Again, first thing is to write down the definition. So we have minus infinity to 0 dx over 1 minus x. So this can be written as limit as t goes to negative infinity, t to 0, and d square root of 1 minus x. Let me just write it down directly in the form. There will be 1 minus x to the power minus half dx. So this is going to be limit as t goes to infinity, negative infinity, my bad, minus 1 over x. So that becomes 1 minus x to the power half divided by half, which is multiplication by 2, divided by minus 1, coefficient of x, which is minus t to 0. That is going to be limit as t goes to infinity. When you put 0, what do you get? You get minus 2, minus of minus plus 2 times 1 minus t to the power half. Now we have to evaluate this limit. Now as t goes to infinity, minus 2 is a fixed quantity, so here is fine. However, this part, as t goes to minus infinity, 1 minus t goes to plus infinity. And square root of that also goes to plus infinity. So the answer is infinity. So therefore, this integral is divergent. All right, let's move on to the next part. D, we have minus infinity to infinity dx over 1 plus x squared. So in this case, we have to break it into two parts, namely limit as t goes to, so first I'll break it from minus infinity to, say, any number of our choice. I'll take 0 square plus 0 to infinity. Now this again I need to write it in the limit form, the definition form. So this is going to be, the first part is limit as t goes to negative infinity t to 0 of 1 upon 1 plus x squared dx plus limit as, now you can't use the same variable, so s goes to infinity 0 to s of 1 upon 1 by x squared dx. Now what is 1 upon integral of 1 upon 1 plus x squared? That is tan inverse of x. So we get limit as t goes to negative infinity tan inverse of x t to 0 plus limit as s goes to infinity of tan inverse of x from 0 to s. Now this is going to be limit as t goes to infinity, minus infinity, tan inverse of 0 minus tan inverse of t plus limit as s goes to infinity of tan inverse of s minus tan inverse of 0. So now we need to investigate tan inverse of t. So how does that look like? So If you want to draw the tan inverse, this is how the graph of tan inverse looks like. So this is value is pi by 2 with a minus sign. This is plus pi by 2, and tan inverse of x looks like so these are the asymptotes for it, horizontal asymptote. So tan inverse of 0 is 0 minus tan inverse of, as t goes to minus infinity, tan inverse of t goes to, as you can see, as t goes to minus infinity, tan inverse is going to minus pi by 2. So minus pi by 2 plus, as s goes to infinity, your tan inverse is going to pi by 2 minus 0. So we get total is pi by 2 plus pi by 2, which is pi. Yeah. So this is your setup, right? So what did you compute by this? You actually computed the area of the following curve, below the following curve. Yeah, this is how your 1 upon 1 plus x squared looks like. So this is what you computed, this area. Okay. So this is the setup for tan inverse. Now let's look at the next problem. Now we are going to discuss a second kind of improper integrals. So consider the following motivational problem. Evaluate the integral of the area bounded by the curve y equals to 1 by square root of x, which looks like this, the red part here. Y equals to 0, which is the x-axis. X equals to 0, which is here. And x equals to 1, which is this part here. So x equals to 1. So we are actually interested in the following area. So we are interested in this area here. So now, if you carefully observe this, here we have a vertical asymptote, right? Now and these points are also finite, right? I mean, like, you're not going for infinity or something. This is your y equals to 0. This was your x equals to 0. And this is your x equals to 1, and you are basically interested in what is in this curve. And you have a vertical asymptote here. Now, suppose I want to evaluate. So to find out this area is same as evaluating integral 1 to x, 1 by square root of x dx. Now, here we have a problem. What is the problem? The problem is 1 by square root of x is not defined on all of the interval. That is not defined at 0. So we cannot use fundamental theorem of integrals, right? Cannot use fundamental theorem of integrals, or fundamental theorem of calculus. Actually, that's what it's called, fundamental theorem of calculus. Yeah, what precisely, you have a to b f prime x dx. And if f prime is continuous on a to b, that was f of b minus f of a. This was your second fundamental theorem of calculus. Cannot use that, cannot use this. Yeah. So why? Because it's not defined at 0. So what we'll do is we'll do a trick. However, we have that 1 by square root of x is continuous. So we know that 1 by square root of x is continuous on 0 to 1, 0 excluded, right? But discontinuous at 0. So we'll define the integral 0 to 1, 1 by square root of x. We'll define this integral to be limit as, since it's not continuous at 0, we'll go close to 0. But 0 from, we are going to close to 0 from this side. So from which side? We are going from right. So this t goes to 0 plus 0 to t 1 by square root of x dx. Now this makes sense. Why? Because for every t, this integral is defined. Okay, so we can compute it now. So let's see what is the integral. What do we get? This is going to be, this is x to the power half, power minus half, so it's going to be x to the power half plus minus half plus 1, which is x to the power half, multiplied by 2, limit as t goes to 0 plus 0 to t. That is going to be, sorry, t 0 should be on this side, right? So this is going to be t to 1, my bad, t to 1. So this is going to be limit as t goes to 0 plus 2 minus 2t to the power half. Now as t goes to 0, this goes to 2. So we say that this limit is 2, or this integral value is 2. So here also we have the concept of convergence. This integral converges to 2. Yeah. So this gives rise to the idea of improper integral of type 2, where you have vertical asymptotes in your function, or you have discontinuity in your functions. That is where we discuss about the improper integral of type 2. So consider the following proper definition. Now f be continuous on an interval a, b, a included, b excluded, and discontinuous at b. So this is how the interval will be. You have a to b. So then you define integral a to b fx dx is integral a, because it's continuous. Instead of going to b directly, we'll approach to via a t. So a to t, where t goes to b, but from where? From the left. So t goes to b minus. And provided this limit exists, then we say that this integral is equal to this integral. So note that this is an extension of your definition from fundamental theorem of calculus 2. Similarly, suppose your function is continuous on a closed interval. So on interval AB, where A is excluded, B is included. In that case, we'll have what? Again, we'll approach to, we have a discontinuity at A, so we'll approach to A via t. So it will be integral A to b f of x dx. Instead of a, you are approaching it via t, and t goes to what? A from the right, so a plus. Again, the improper integral a to b fx dx converges if the corresponding limit exists, and is divergent if the limit does not exist. We'll see example of both in a moment. So if the discontinuity is at the end point here, or on the this endpoint of the interval, we have defined it. What if the discontinuity is in between? So suppose you have a to b, and you have discontinuity in between. In that case, what will you do? You will split the discontinuity, right? So you will basically, so scenario A is you have so for first scenario, you have integral A to B, and you have an asymptote like that. For scenario B, we have a discontinuity of this form. There's some value at this guy. This is B. And then scenario C, what we do is we break it into two parts like this. So we go from A to C, and then C to B. So this is how we deal with it. Okay, so we break it into two parts. This part will be dealt from here, and this part will be dealt using the techniques from here. Okay, so we split the discontinuity. So let's see an example of this. So let's do problem A. So A. So first of all, if you look at A, first of all, let's see, is it continuous? No. Where's the problem? The problem is at 2, and 2 is what point? Is this point here, right? So you have 1 to 2, and this is your point 2. So this is going to be 1. So 1 to 2 dx over x minus 2 square is going to be written as limit as you want to approach to 2 now, right? But from where? From you're approaching where at t, and your t approaches from left. So integral 1 to t, and t approaches to 2, but from left, of 1 by x minus 2 the whole square dx. Now, what is this equals to? This equals to limit as t goes to 2 minus, what is the integral of this? Minus 1 upon x minus 2, 1 to t. That is going to be limit as t goes to 2 minus 1 upon t minus 2 minus 1 upon 1 minus 2. So now as t goes to 2 minus, so this will be fixed, which will basically be 1. So we have minus 1, 1, so plus 1. However, this guy, the top is fixed minus 1, the bottom t goes to negative 2, t minus 2. So if you have t goes to negative 2, sorry, t goes to 2 from left side, your t minus 2 is less than 0. So the whole thing has a positive sign, and you get the limit is going to be infinity. So therefore, this integral diverges. Let's look at part B now. So we have 0 to 2 dx over 2 minus x to the power 2 by 3. Now, where's the problem? The problem is when the denominator becomes 0, which means x equals to 1 by 2. So this is 1 upon 2 minus 1 to the power 2 by 3 is discontinuous at x equals to half. So since the discontinuity lies in between, my integral can be split into 0 to half dx over 2x minus 1 to the power 2 by 3 plus half to 2 dx over 2x minus 1 to the power 2 by 3. Now this side has to be, so we are, what in the first part we have the following. In first part we have 0 and we have half. In the second part we have half to 2. So in this case we are approaching from this side. So what will the integral look like? So integral is going to be limit as t goes to half, but from which side? From the left. So minus 0 to t dx over 2x minus 1 to the power 2 by 3. And in this case, we have limit as s goes to half, but which side are you approaching? From the right. So half plus s to 2 dx over 2x minus 1 to the power 2 by 3. Now, what is this integral? Let me compute this integral. So 2x minus 1 to the power minus 2 by 3. And what is the integral of this? This is going to be 2x minus 1 to the power minus 2 by 3 plus 1, which is 1 by 3, divided by 1 by 3, which is 3, divided by the coefficient of x, which is 2. So this is going to be limit as t goes to half from minus, we have 3 by 2 times 2x minus 1 to the power 1 by 3. Limits are 0 to t. And in this case, limit as s goes to half plus 3 by 2, 2x minus half to the power 1 by 3, s to 2. Now it's time to put the limits in. So we get limit as t goes to half minus 3 by 2 times 2t minus 1 to the power 1 by 3 minus 3 by 2 times minus 1 to the power 1 by 3 plus 3 by 2 times 4 minus 1 to the power 1 by 3 minus 3 by 2 times 2s minus 1 to the power 1 by 3. I forgot to write the limit here. Let me push it in half plus. Now let's compute it. So what do we get in this case? We get as t goes to minus half, this will go to what? 0. So we have minus 3 by 2 times minus 1 to the power 1 by 3. In this case also, you get 3 by 2. So 3 by 2 times 3 to the power 1 by 3 minus, as s goes to half plus, this will also go to 0. So the answer is minus, so we get minus becomes plus, so 3 by 2 times 1 plus 3 to the power 1 over 3, and this is your answer. So it is convergent. Yeah, not only it's convergent, you know the value of this integral as well. The next integral we want to deal with is c, which was 0 to 1 ln x dx. Again, where is the problem? Ln x is not continuous at 0. Yeah, so that's where the problem is. So again, we are here 1 and the problem is at 0. So we'll approach to 0 from this side. So this integral is going to be limit as t goes to 0 plus t to 1 of ln x dx. Now, if you recall, or if you apply integration by parts, you will see that this integral is going to be x ln x minus x 1 t to 1. So you can do that by parts. And this is going to be limit as t goes to 0 plus. Now time to put the limits. So when you put t, you get t ln t minus t. And then when you put 1, you get minus 1 ln 1, which is 0, plus 1. So now we have to compute these limits. So first of all, let's compute this limit here. So what is this limit? So if you look at this, so let's compute this limit separately here. So limit as t goes to 0 plus of t ln t. We want to compute this limit. Note that this is of form 0 times minus infinity. So you can apply the L'Hopital's rule. So this is going to be limit as t goes to 0 plus. Let's write it as t. Let's write it as ln t divided by 1 by t. Because for L'Hopital's rule, you need a f of x divided by g of x, and this is going to be of this form, right? Then by L'Hopital's rule, or L'Hopital's rule, this is going to be limit as t goes to 0 plus derivative of ln t is 1 over t. What is derivative of 1 by t is minus 1 by t square. And with little bit of rearrangement, you can see that this is going to be limit as t goes to 0 plus of minus t, and that is 0. So therefore, this limit is 0. The other one is also 0, minus ln 1, which is also 0. And then we get what? When you put 1, you get, so hold on a second, I interchanged the limits. So this must have been t to, so it's basically t to 1. So this should have been other way around. So let me put a minus sign here. And so let's interchange this. So this is going to be t ln 1 1 minus 1 minus t ln t minus of mine. So we get another this. So we get minus t. And so this is going to be 0 minus 1 minus 0 minus 0. So this is going to be minus 1. Sometimes we are happy just to know if integral or improper integral is convergent or divergent. So here's the idea. So suppose you have f and g as continuous function with g always less than f of x. So you have the following: your g of x is less than f of x as given in this graph here, right? This is your g here, and your f of x is always bigger. So now, if integral of f of x dx is convergent, what does it mean? It means that if area under the f is infinite, is if this is convergent, this means if area under the f is finite, this implies area under g of x is also finite, right? So that means what? If the integral a to f of x dx converges, then integral a to infinity of g of x dx also converges. So if this improper integral, the bigger one, converges, then the smaller one, which is dominated by this, also converges. B, if this area below g is infinite, integral area under f of f is going to be already infinite then, right? So it means what? If area under g of x is infinite, that is, it means it diverges. This implies the area under f of x is also infinite, right? Because f of x area is bigger than area below the curve f of x is bigger than the area below the curve g of x is also infinite. So therefore, therefore integral a to infinity f of x diverges. Okay. Now note that there is another case. Suppose integral, if this guy diverges, you can't say anything about area below this, right? It could converge or diverge. Okay. So let's look at an example. So here, let's look at problem A. Use comparison test to determine if what? If the area, if the following integrals are convergent or divergent. Forget about area, just the integrals themselves. Okay. So now, let's see. So first of all, let's see where is the problem here. Is it continuous? Because what do we need? We need f and g to be continuous, right? So ln x, where is ln x discontinuous? So this guy, ln x minus this function, 1 by ln x minus 1 is discontinuous at, of course, here the domain is x greater than 0, is discontinuous at what? When at ln x equals to 1, this implies x equals to e, which is roughly 2.71 something. So therefore, what? 1 by ln x minus 1 is continuous on 4 to infinity. Now we want to use comparison test to see if it is, or comparison theorem to see if it converges or diverges. Now note that you couldn't have integrated it directly so you can't say this is cannot be integrated in terms of, so this cannot be integrated in terms of elementary function. This cannot be integrated in terms of elementary function. So otherwise we could have used the definition directly and need not have to use the comparison test. But since this cannot be integrated in terms of elementary function, we have to use some kind of comparison test to determine it converges or not. Okay. So now, so notice the following. So let me draw 1 over. So let me look at, so ln of, this is how ln of x minus 1 looks like, shifted down. So this is basically 2. Sorry, this is basically e. And y equals to x looks like this, right? This is your y equals to x. So this function is smaller than y equals to x. So if you take 1 over that, you will see that x is greater than equal to ln x minus 1 for x greater than equal to 4. So 1 over x is going to be less than equal to 1 upon ln x minus 1 on 4 to infinity. So now we need to see. So the idea is that you don't choose this directly. We have a plan in mind already that this is going to diverge. So we'll discuss it very soon, how to check that out. So notice that integral 4 to infinity, and this is of course greater than equal to 0, and they are continuous as well on this part. This is strictly greater than 0. So integral 4 to infinity 1 over x dx is limit as t goes to infinity 4 to t 1 by x dx, which is limit as t goes to infinity ln x 4 to t, which is going to be limit as t goes to infinity ln t minus ln 4, and this goes to infinity, right? So this diverges. So diverges. So if this diverges, then by comparison test, therefore by comparison test, integral 4 to infinity 1 by ln x minus 1 dx also diverges. Okay, so this is how the also diverges. Yeah, so you have to mention what test you're using, which is the comparison test. Okay. So 1 over ln x. So the idea was we had a 1 over ln x diverges. In fact, this is something you should prove at some point. So here's the homework, or here's something we should prove. Integral 1 to infinity 1 by x dx, or 1 by x to the power p, converges if p is greater than 1, and diverges if p is less than or equal to 1. Now this is a big point because this helps you to compare with the function already. So when I look at ln x minus 1, I'm interested roughly in ln x. So I know that 1 by ln x is bigger than 1 by x. So we already had that strategy in mind before we went further. So I already know 1 over x is integral 1 over x from 1 to infinity is divergent because of this theorem here. And this theorem is not hard to prove. So we should prove this at some point. Let's go on and look at the next problem. 1 to infinity of e to the power minus x squared dx. So e to the power x minus x squared by 2, or minus x squared at least, looks somewhat like this. So e to the power minus x squared. So I suspect that this function will converge. So I want to find a larger function than e to the minus x squared, which will converge as well. So note e to the x is less than equal to e to the power x squared by 2 for x greater than equal to 2, right? As why? Because x squared by 2 is greater than equal to x for x greater than equal to 2, and e is an increasing function, right? E to the x is increasing function. Why? Because the derivative is positive. So if x squared by 2 is greater than equal to x, and e to the power x squared is greater than equal to e to the x. Now because we have minus sign, this would imply e to the power minus x squared by 2 is less than e to the power minus x. But this is only true for x greater than equal to 2. Our integral starts with 1, but let's first prove. So consider 2 to infinity of e to the power minus x dx. Yeah, so we'll prove at least for 2 to infinity and then see later on what happens. So this is going to be limit as t goes to infinity of 2 to t e to the power minus x dx. This is going to be limit as t goes to infinity. Now what is the integral of e to the power minus x? It is e to the power minus x divided by x. So e to the power minus x 2 to t. This is going to be limit as t goes to infinity e to the power minus t plus e to the power minus 2. Now as t goes to infinity, note that 1 over, this is same as e to the power 1 by e to the power t, right? This goes to 0. So we have this limit is equal to e square, which converges. This means what? This means, therefore, integral 2 to infinity e to the power minus x square by 2 dx converges. Why? Comparison test. This converges. Now we have 1 to infinity, sorry, 1 to 2 e to the power minus x squared by 2 dx is also a finite number. We have seen this when we were bounding it. If so, you can prove it if you want by basically noticing that e to the power minus x squared by 2 is, since we have this as a decreasing function, this will be between what? This will be between some powers of e, right? So what is the lowest power we get? 1 by, so since we are looking at negative power, so the bigger the negative power, so we have, this is going to be 4 by 2. So this is 1. So when you put 1, you get 1 by 2. So your E is bounded between this, and therefore, if you recall, we had the bounds. Therefore, this is going to be 2 minus 1 less than equal to integral e to the power minus x squared by 2 dx less than e to the power minus half 2 minus 1. So this is also, this is bounded and is a finite number. So this is a finite number. This converges. This is also finite. So finite plus finite is a finite number, right? Therefore, we can conclude that, so this is convergent. This guy is convergent. Therefore, 1 to infinity of e to the power minus x squared by 2 dx is convergent, because you're adding two convergent integrals and their sum is convergent.